Okay, so I want to start talking about how to use Venn diagrams for um, categorical statements. And Venn diagrams are really useful. They're a really pretty powerful way to model these statements. I think they're good for helping us understand A, what categorical statements mean, but B, they're going to be really useful in seeing whether categorical arguments are valid. So let me give you guys an example, right? All A are B. Universal affirmative, universal affirmation, right? All cats are mammals, you know, all squirrels are mammals, so on and so forth, right? All birds are warm-blooded, right? All A or B. Everything in this A category is in this B category. And the idea of Venn diagrams is that we can draw little circles to see what these statements mean, right? All A or B. So what are we saying when we say all A or B? We're saying that there is nothing in this A circle that's not also in the B circle. Let me label the A circle since, you know, in a minute we're going to color in a lot. So we look at A and B. Well, there's a lot of the A circle outside the B circle. There's a lot of the B circle outside the A circle, but there's this space where they overlap. When we say all A or B, what we are saying is there's nothing that can fit into this category of A things that's outside the B circle. Everything in A is going to overlap with B. Well, how do we model that? Well, with Venn diagrams, we just color in all the A circle except where it overlaps with B. We are showing that there is nothing in A that is not also in B. Black it out to show that there's nothing that can fit in here. All A are B. Well, all right. So what about no squirrels or people, right? No mammals or lizards, so on and so forth. Well, with this other one, we wanted to show that everything that's in the A circle in the A category is also in the B one. So we black out everything here except for the overlap. So what are we going to do if we have, let me draw them bigger. I should have done that for the first one. Well, what are we saying here? We are saying that there is nothing can fit in this space where A and B overlap. No A or B looks like this, right? We black it out to show that nothing could fit in here. It is empty. Nothing is going to go in here. This is what no A or B looks like. All A or B. We're going to show that everything has to be, if it's in the A category, also has to be in B. But for this other one, the no A or B, we show, I'm not going to be too extra about filling this in just to give you guys the idea. If we wanted to put anything in A, in the first one here, we know it would also have to go in B, right? In the second one, if we wanted to put anything in A, well, we know it couldn't go in B no matter where we drop it, right? All right. So what about sum statements? Well, remember what sum means? Sum means at least one. So we know that there is something in this space, at least one, maybe more, in this space where A and B overlap. We'll just put this X here to show that there's the one thing, right? And it really doesn't matter how you represent this. You could also, if you don't want to use an X, you know, a dot would be fine. You want to be really whatever, you could do a little star just to show that there is at least one thing in this space where these two overlap. Finally, some may or not be. Well, how would we draw that? Well, think about it. We want to show that there's at least one thing in this category, this group of A things that's not in the B group. Well, we just draw our little X or whatever outside here in A. Now, you guys might have noticed that I used one statement Slappy as a squirrel. You know, how do we use or how do we handle these singular statements? X is a Y, or better, X is, we're saying that there's this one singular thing that's in this A group. Well, if we were going to do this, the way we would handle it is just we might label it. This is just saying, well, Slappy is a squirrel. Well, there is at least one thing that's called Slappy that's in the squirrel group, right? So we can just handle these statements that way. You don't have to always label them, right? But if you see these singular X as a whatever statement, this is the way we'll handle it. There's some ways of doing this in categorical logic that are a bit more roundabout, a bit more involved, a lot bigger pain in the neck. Don't worry about it. Now, I want you guys to notice one more thing before we wrap this up. With some categorical statements, it matters what the order is. All A or B. All right, I'll draw the A out there so you know that's the circle. Well, if all A or B, what I'm going to do, I should have drawn this smaller, make my life easier, but whatever. What I'm going to do is black out all the A circle that is in the B circle. Sorry, all the A circle that's not in the B circle. And so if this is true, there is nothing, you know, if I now told you, you know, if I want to put anything in the A group no matter what, it has to land in the B group because that's all that's left open. The only things that can go in the A circle have to fall in the B circle because the rest is blacked out. But there are for all that this statement says, there are all these things in the B group that might not be in the A group. If I talk about something in B, it might be out here, does not have to be an A, right? Now notice if I say all B are A, well, that's going to look really different, right? That's going to look like this. And this is saying there is nothing that can be in B that's not also an A. But there's lots of ways for things to be B and B and not an A, right? And you can think about this, right? If I say all cats are mammals, well, that's true, right? All things in the cat category are going to be in the mammal thing. But if I say all mammals are cats, that's obviously not true. There's lots of different kinds of mammals. With all statements, the order matters. But with our universal negative, the no statements, the order does not matter. No A or B. That's going to look like this. We're saying that there's nothing where these two overlap. And, if I had no B or A, it's going to look exactly the same way, right? I mean, my circles are different sizes, but the diagram's going to be the same. When it comes to sum statements, well, it's going to be slightly different, right? With sum statements, sum statements, well, let's look out for sum statements, right? Sum A or B. Well, how would that look? Well, we draw something here where A and B overlap. Well, what does it look like here? Sum B or A? Well, same thing, right? So with sum, with particular affirmation, order doesn't matter either. Sum A or B, the diagram for that looks exactly like the one for sum B or A, right? And if I say some cats are mammals, well, it is then definitely true that some mammals are cats. But now notice this. What's that look like? Notice some A or not B would be consistent with all B are A, right? Some mammals are not cats. but all cats are mammals, right? We don't know that that's true. All this is telling us is that there is at least one thing in this A category that's not in B. There could be lots of things that are both A and B. That's possible. We could put stuff in here. There could also be lots of stuff that are B but not A, but we don't know that that's true. Anyway, but notice some B are not A looks very different, right? Telling us the first one tells us there's at least one thing in the first category that's not in the second. Um, sorry. The second one tells us there's at least one thing in B that's not in A. Different statements. Now, this is important because this is, A, it just, when you're doing all or some or not statements, be very careful with the order. It matters. When you're doing some are or no are statements, the order doesn't matter. So this little symbol here, this 3 lines logical equivalence, we'll talk more about that. These statements mean the same for purposes of logic. That's what these 3 lines mean. These statements mean the same thing. These statements do not. Logical equivalence just means for the purposes of logic, statements mean the same thing. We'll talk about more precise definitions of this later. But for these, some A or B logically equivalent means the same thing as some B or A. Order doesn't matter. No A or B means the same thing as no B or A. But all A or B does not mean the same thing, not logically equivalent to all B or A. The same goes for some A or not B and some B or not A. Okay, so we will stop there. Hope you guys are getting a basic idea how to use these Venn diagrams. Now, one thing that makes Venn diagrams easier to use than Euler diagrams is that they have these very precise rules, which we're already talking about. I will say more about those in the next lecture. All right, so we will bring this to a close. Next lecture, I'll talk about how to use Venn diagrams to evaluate validity.